Okay, class, picking up where we left off at, we had log of 27, which I said you could enter into your calculator, and that will give you 1.4313636764. And of course, the number is longer than that, but we know this base is 10. So if we took 10 to this power, it would give us 27, or very close to it. So this is our final answer here. So now we scroll to the next page. It says properties of logarithms. It says recall, y is equal to log base b of x, which leads us to b to the power of y is equal to x. Now this x here is our argument. Okay, so now, what numbers can act as the base of the logarithm function? Now, first of all, your base has to be greater than 0. So that's any positive number. It says what numbers can be in the argument of the logarithm function? Only positive numbers. Can have a log taken of them. It says for any allowable base, log base of 1 is equal to 0. Again, for any allowable base, log base of b is 1. And for any other allowable base, log base of b to the n is n. Now, as long as you're using a proper base or allowable base, these statements are always true. Remember that base must be an allowable base. Now we go here to example 3. It says use the properties to help find the following logarithms exactly by hand, if possible. Log 6 of 1, we know based upon what we just learned, that must equal to 0. Log 3 of 81, let's change 81 to have a base of 3. So this would be log 3, and we know the base, an exponent that gives us 81 with a base of 3 is 3 to the 4. So this is the same as log b of b to the n, which we know is equal to 4. Now log base 4 of 4, we know is equal to 1. Log base 7 of 7 to the 8th, we know is 8, because this is the same rule that we just talked about with b. Log 2 of 1 is basically the same as a, which gives us 0. Log 2 of 8, now we could change this 8 to an exponent. So it'd be log 2 of, give this 8 a base of 2. And we know 2 to the third power is 8. And we know this is the same as log b of b to the n, which will give us the n. Log 9 of 9, we know is 1. Log 16 of 0. We cannot do that because remember, this argument here must be a positive number. And we know that 0 is neither positive or negative. So this answer here is undefined. Now log 5 of negative 25, again, just like h, this argument here must be positive, and it is not, so it's undefined. Now, or you could put error. Okay, so now these are the answers that we have for A through I. Now, what happens is this here. We can rewrite these as exponents. I'm just going to do about 1 or 2 of these just to prove this to be correct. So we could write this. This would be 6 to the 0 power. And doesn't it equal to 1? We could do this here. Doesn't 3 to the 4th power equal 81? We know 4 to the 1st power is equal to 4. And so on. Now when we get down here to H, 16, can you think of anything 16 to any power that would give you 0? There's no such thing. Can you think of 5 to any power that will give you negative 25? There's no such thing, no such number. So that's why it's undefined or an error. Now it says here, using the inverse nature of logarithms and exponential functions. Always remember that logarithmic and exponential functions are inverses of each other. Find the inverse of each function. Now we have f of x is equal to 6 to the x power. Now to write this as an inverse, you know we will write this as f inverse of x. And we need to write this exponent as a logarithm. So it would be log base 6 of x. Now we have b, g of x is equal to log 8 of x. So we want to rewrite this as an inverse. So we have g inverse of x is equal to h to the x power. Now we go here to c. We have h of x is equal to 2/3 to the x power. So we do the inverse of h. And then that will give us log base of 2/3 of x. Now we have k to the x is equal to log x. So we know the inverse of k to the x is the inverse of k of x. And then that will give us 10 to the x power because we know this base is 10. Now we scroll down here to example 5. It says create a table of reasonable points and then graph the function. F of x is equal to 2 times log 3 of x by hand. Now I took the liberty of putting in some points here because we know we didn't want this shifting all over the place. So we put in, we have x and we have f of x is equal to 2 log base 3 of x. So we know if we put in 1, that will give us 0 overall, which is shown here. We put in 9, we know log base 3 of 9 is 2. And we add 2 times 2 is 4. And then 1/3, 1/9, and 3. We want numbers that will come out clean here. So this would be 1, 0, which you have here. We have 9, 4. Then you will have 1/3, negative 2, which is about here. 1/9, and we had negative 4, which is about here. And then we will have 3, 2. Now it says here, this is clearly the inverse of some exponential function base of 3. Because if you look here, if we draw our line here, again, if we draw our identity line here, we know that the inverse graph will go this way as well. So now we scroll to the next page. Now we want to use logarithms in science. It says, remember that logarithms were first used by scientists such as John Napier. That's because logarithms make it more convenient to discuss and compare very large or very small numbers. Examples include decibels, Richter numbers, pH scale, etc. Now you all have one extra parenthesis in here that I do not have here. You all had after very small numbers, you had a parenthesis as an astronomer. Napier was working with large numbers a lot, and then period. Okay, so this is slightly different, but basically the same. Now we go here to Richter number. Seismologists measure the amplitude height of seismic waves, disturbances in the ground. The amplitude of the smallest measurable seismic wave is called the reference amplitude, and we write it as A of 0 or A of O. When an earthquake occurs, the seismic waves are measured and described by stating how many times larger than the reference amplitude they are. The size of the earthquake is then described using the Richter number. R is equal to log A of 0. Now, example 6. Now, well, first of all, let's designate this. This A in your numerator is the amplitude, I want to abbreviate this, of the quake. And then here at the bottom, this A of 0 is the reference amplitude. Now, it says here, example 6, suppose there were three earth tremors, seismic waves for the measured. First tremor is 1,000 times the reference amplitude. The second tremor, 10,000 times the reference amplitude. And the third tremor, 100,000 times the reference amplitude, giving us A over A of 0. Now, it says find the Richter numbers for these tremors. So now we have to go through. So we have, first of all, we will have the first tremor. That's A is equal to 1,000 times A of 0, because it's 1,000 times the reference amplitude. Now, so we will have R is equal to the log of 1,000 A of 0 all over A of 0, because we substitute. So these A of 0s will simplify out, and we have the log of 1,000. Now log of 1,000 gives us 3. Now we go to the next one. We will have A is equal to, remember the next is 10,000 times the amplitude. So we would do the same thing. Let me just draw this little line to separate them. So we have R is equal to log 10,000 A of 0 divided by A of 0. Now we know these A of 0 simplify out to 1. So we know this would be 10,000 times 1, which is 10,000. And we know 10,000 divided by this 1 here will leave us 10,000. So the log of 10,000 gives us 4. Now we go to the last one. It's the same thing, except for this time we use 100,000 times A of 0. So we will have R is equal to log 100,000 A of 0 all over A of 0. These simplify out, and we will have log of 100,000, and that will give us 5. Now remember, these have went up by a power of 10. So for every power of 10, you go up by 1. So let's scroll down here. It says example 7. It says in 1960, the largest earthquake ever recorded occurred in Chile with seismic waves measuring 3.16 times 10 to the 9th power times the reference amplitude. The largest earthquake ever recorded in the lower 48 states happened in Fort Tejon, California in 1857 with seismic waves measuring 7.94 times 10 to the 7th power. Find the Richter number of both earthquakes. Now we know that both of these are in reference to the reference amplitude, just like the 7.94 is also. So what we would do is we would say the Richter of Chile is equal to log